hear mostly, you'll hear mostly only call signs, that sort of thing, with the phonetic alphabet. Minimize that. Okay, how many licenses can you get, basically? How many operator primary station license grants may be held by one person? One. What proves that the FCC has issued you a primary or operator license grant? This is one of the questions.
Just to jump in, Jim,
Yep.
I'm not seeing the slides well. I don't know if it's just me, but I see what looks like the slide master. I don't see the individual slides.
What about everybody else?
Same here, same as Dave. It
Yeah,
looks
just
like
the one that you're showing, just the one you're showing right now is blank, but when you go to the next slide, there's writing on them. This one doesn't have writing on it.
it looks like you're making slides. We're not actually watching the show.
Let me, yeah, I think what happened, let me,
You have dual monitors, maybe?
no, what happened is I think it, okay, now let me go back and just restart this
Yeah, from the, yeah, there you go. There you go.
slideshow from the beginning. Okay, we back now?
There you go.
Okay, there we go. Yep. So let me skip down to where we were. Yeah, I think what it did is.
There we go.
Yeah, so we got to the operators, right? Okay. And this is a question, how do you know you've taken your test, you passed the exam? How do you know when you can start using your radio? The key here is when the license appears in the FCC database. And this will show up again in another question, actually. What does the FCC Part 97 definition of a beacon? Well, think about what does a beacon look like? Or what do you usually think of as a beacon? That's sort of a flashing light or something. Something is continuously sending out a message. And in this case, from the FCC standpoint, it's an amateur station transmitting communications for the purposes of observing propagation and related experimental activities. This is the wording right out of the FCC. In this case, you sort of have to think, well, if you've taken enough practice tests, you'll recognize what the right answer is. But some of these say, well, gee, C might be, that's about amateur bands, isn't it? Not, it's a possible answer. National emergency bulletins, well, you know, some of the other answers are more subtle than others. And so you'll get to know what the right answers are. Okay, what's the FCC Part 97 definition of a space station? Well, all of these look like space stations, but from the FCC standpoint, it's any station located 50 kilometers above the Earth's surface. Now, if that answer B, the manned space station, had an amateur radio in it, that would fall into the C category, the correct answer. And one of the fun things to do with amateur radio is you can communicate with the International Space Station. And people do it all the time, and it's not all that difficult. Which of the following entities recommends transmit and receive channels and other parameters for auxiliary and repeater stations? Now, the FCC allows or allocates certain frequencies bandwidth to amateur radio. And so the question is, how do you prevent everybody from wanting to use the same frequency? And the FCC doesn't do this, but this is done by amateur groups in each region. So you have a group of coordinator supported by local amateurs who collectively decide how can we best allocate the resource or the frequencies in our area. In the case of Western Washington, the group is called WWARA, the Western Washington Amateur Relay Association. And this is a group that puts out a list of what frequencies should be used for what purposes within the amateur bands within Western Washington. And it's a voluntary organization, but amateur radio operators follow that pretty well. In other words, everybody looks out and makes sure they're not using a frequency that shouldn't be used for a particular purpose. And who selects the frequency coordinator? Now, if you figured out that it's a voluntary group, then you can pretty quickly come to the answer C, amateur operators in the local or regional area. So it's the local group just deciding how to best organize the frequencies. And when you learn about repeaters, you'll understand why the frequencies have to be allocated, and that'll be in a later section. What is the Radio Amateur Civil Emergency Services, RACES, as we call it? Now, the key here in figuring out the correct answer is civil defense. And you can see all these have civil defense communications in the question, in the answer. And indeed, they are all correct definitions, parts of the definition of the RACES, the Civil Emergency Service. And the last question in this section, section 1, when is willful interference to other amateur radio stations permitted? Now, willful interference doesn't sound like anything that should be allowed, and it isn't. And this is one thing to keep in mind, is that there can be very stiff penalties for interfering on the radio. If you're using your amateur radio and you're interfering with other stations, I've seen FCC fines on the order of $20,000 and loss of license. So it's not something to trifle with. So keep to the rules. Okay, that was the first section. More of same. Now this is going to be on frequencies. Now some of these, you just have to learn what the frequency is, but I'll show you a chart. For example, the first question is, which of these frequency ranges is available for phone operation, the voice operation by a technician license? This is a chart you can download from the ARRL website. It's the amateur radio frequency bands. And this, if you look at this closely, you can find the answer to these questions. In this particular case, you can see the arrow, Heparin 10 meters. There's a little yellow chunk, which corresponds to 28.3 to 28.5. Which amateur, back to the space station, in the International Space Station, which amateurs may contact the ISS? Basically, anybody with a tech class license or higher. That's, again, one of the fun things is that you can go out in some cases with a handheld radio, like a walkie-talkie, and you can communicate with the International Space Station. Okay, what frequency is the 6 meter amateur band? Now, frequencies, this is a key thing to learn. It'll come up a lot. 300 is the magic number. To convert frequency to wavelength and vice versa, divide whatever you're using by 300 by whatever you're using. In this case, as an example, 300, if it's 2 meters, 300 divided by 2 is about 150. The actual band for amateur radio is 144. We'll see how that works here. 6 meters, 300 divided by 600, or excuse me, 300 divided by 6 is 50. 52 is the closest frequency in this case. Now 49 is even closer, but in this case it's 52. And again, this is another one of those that you sort of have to know the answer. Again, another example of the formula, 300. 300 divided by about 150 is 2. So that should be 2 meters. Yep. How may amateurs use the 219 to 220 megahertz segment of the 1.25 meter band? Now, this is the one you have to know by looking at that chart. If you looked at that chart earlier, you'd see a tiny segment of that band, 219 to 220, specifically labeled for fixed digital message forwarding systems. You just have to learn this. This is not something you can figure out. Now you can certainly memorize the chart, but there's an awful lot of information on that chart. Which HF bands does a tech class operator have phone privileges? 10 meters only. Again, going back to that band chart, the only one that says technician of these frequencies here is 10 meters. And again, 10 meters is the wavelength. Which of the following VHF, UHF band segments is limited to CW only? Again, you just have to, for example, look at the chart, remember, and tiny segments of both those bands are allocated for CW. CW is Morse code. How are US amateurs restricted in segments of bands where the amateur radio service is secondary? Now, I mentioned earlier that the FCC allocates frequencies. In some cases, they allocate frequencies to more than one group. For example, you all have heard about 5G, the new cell phone frequencies. Amateur radio actually has a tiny portion of the 5 gigabyte spectrum, but it's not major. And in some cases where the FCC says the amateurs can use this band, but you're secondary, you don't want to mess with somebody else who's got primary use. Although don't interfere with them. And we already heard problems with interfering if you violating the FCC rules. Why should you not set your transmit frequency to be exactly at the edge of the band? Now we saw earlier, for example, at 10 meters, it was 28.3 to 28.5. So why wouldn't you want to be at exactly 28.5? Well, let's see, because your frequency display might not be right. Others, your transmitter might be saying you're at this frequency, but it might actually not be. In some cases, there are side bands to the frequency, which can extend beyond the edge. Frequency drift, you start out at one frequency and it drifts off. So all these are reasons why you shouldn't be right at the edge of a band. And where may signal sideband, SSB, a signal sideband phone be used in the amateur bands above 50 meters or 50 megahertz? And again, this is just something you have to know based on the FCC rules. Now this basically says that doesn't specifically apply to technician, but in general, that basically there's some segment in all bands and what we call the HF spectrum. What's the maximum power you can use in the HF segment? And that was only 10 meters, 200. And again, another one you just have to learn. In this case, for frequencies above 30 megahertz, 1500. Okay, that's the second part. And then just zipping on through, this is more about the license, getting your license specifically. What are the license classes currently? There are currently 3 license classes: technician, which is your first level, the general, and then the amateur extra. There had previously there have been advanced classes and novice classes. And who may select the desired call sign under the vanity call sign rules? Basically, anybody can have a vanity call sign. You know, a vanity call sign, if somebody's named Bob, they would see if they could find the call sign W7BOB. If that's available, then you can get that. Most of us, well, a lot of us, my call sign just is what came out of the system, AE7UQ. What types of international communications are an FCC licensed amateur radio station permitted to make? Just basically where the communications are incidental purposes of amateur radio service and remarks of a personal nature. Again, this is wording right out of the FCC rules. Again, note in B, one of the things you can't do on amateur radio is conduct business. And the other thing to always remember about amateur radio is it's a public airwaves. So whatever you're saying over the radio, anybody else with the radio on that frequency can be listening into. What happens if the FCC is unable to reach you by email? And emails is a new addition. When I got my license about 10 years ago, you didn't have to put an email into it. It was just a mailing address. But they're emphasizing emails now. And if they can't reach you by email, you can lose your license. So that's a requirement for applying and getting your license now. What sort of license call sign would you get now if you get your technician license on the 24th when the testing is coming up? Currently, this is the format. If you got your license next month, it would probably be a KK7 call sign, KK7 ABC, something like that. And they just sort of work through the alphabet. When I got my first license 11 years ago, I got KF7.
Jim,
Yep.
we have some people here that are not from the 7 call area.
Okay, so it would be, it depends on the call area, the area of the country. The country is divided into 10 different zones for amateur radio, and what the prefix letters would be sort of depends on how many licenses are issued in that area. So it might be a KC or a KD or a KQ, whatever. It depends on what's happening in that particular area of the country. But in our area, if it happens to be Western Washington or in the 7 area, which is pretty much the northwest of the US, then it would be a KK. From which of the following locations may an FCC licensed amateur transmit? Basically, the intent here is to show you that you can, as long as you're in a boat you're in international waters and on a US registered documented, you're a US vessel, then you can use your license. Which of the following, here we go, this is going to be a reminder, which of the following can result in a revocation of the station license or suspension of the license? Well, what did we just learn? Failure to provide or maintain a correct email address. So they're really putting an emphasis on this. What is the normal term for an FCC license? Currently 10 years. What's the grace period? In other words, you've got 10 years, you have to renew it within, you can renew it within, I think, 90 days before it expires. If you let it lapse, you do have a grace period of 2 years. How soon after passing the license exam may you transmit on the amateur radio band? We know the answer to this one, don't we? License C, item C, as soon as your license grant appears in this database. And the last question for this section, if your license is expired and is still within the allowable grace period, which we just learned was 2 years, may you continue to transmit on the amateur bands? And the answer is no. As soon as your license is expired, you cannot transmit on the amateur bands, but you have 2 years to renew it. And so, yes, you can after your license had been renewed. Okay, that's a quick run through of the first 3 sections of part 1. We're pretty much on track, at least for getting this done, since we had a bit of a slow start. Any specific questions on these? Again, these are pretty much the rules. And so there's not really a lot of theory to think about here. Okay, well, I will stop sharing.
So
It's my
Dan,
turn?
can you share? Yep, go.
Yeah, let me go for it. Let's see, let me find it here. Here we go. Aha, and let me find the play. Okay, y'all see that now?
Yep.
Okay, we're gonna change things up a little bit here. We're gonna talk, instead of just rules, we're gonna talk about the very fundamentals of electricity, how electricity works. And if you're a double E or somebody, an electrician even, you could probably go crack a beer right now. But for the rest of you, hang on and we'll go through some of the basics here. And some of the stuff is going to be built upon as you go further into your amateur career, let's say studying for your general or extra class license. We're going to cover sub-element T5 of the exam pool. So here we go. Let's see, is this going to work? Yeah. Okay, let's talk about the elements and properties of electricity. Electricity is caused by a flow of electrons going from a positive charge through some kind of conductor and ending up back in a negative charge on the power source, whether that be a battery or a generator, alternator, or anything like that. So, be aware of that. It's a flow of electrons. And the electrons themselves don't go all the way through the circuit, but there is a pressure of electrons that do. So let's talk first about the pressure, which is what we call the voltage. In the math that we do, the math that's on the question pool, we typically use the letter E. Sometimes you might see the letter V, but typically the letter E. For a current, that's basically an expression of the flow of electrons. So just like water has the pressure if it's coming out of a hose, let's say current has a flow. They use the letter I. That's basically for intensity of the current. And then there's one other property called resistance. And that's basically in a circuit, that's the opposition to the flow of electrons. And that's also a quantifiable amount. So we're going to be reviewing the very, very basic mathematical relationships between these that you need to know to pass the questions in sub 5. Let's first talk about voltage. It's also called the electromotive force. That's the technical term for it. That's why they use the letter E in the formulas. It's often called EMF, or the pressure. The unit of measurement is the volt, and it's measured with a voltmeter. The volt, just as an aside, was named after the Italian physicist Alessandro Volta, who lived from 1745 to 1827. This is a historical thing. Now we'll talk a little bit about the current flow. That's the flow of electrons in a circuit. It's the intensity of electron flow. It's measured in amperes, and that unit of measurement was derived from the French mathematician André Marie Ampère, who lived between 1776 and 1836. And we measure that with an ammeter. Resistance, that's the quantification of the opposition to current flow in a circuit. The unit of resistance is the ohm. That was named after the German physicist George Ohm in 1861, and it's measured with an ohm meter. So we got those three properties. Electricity is a form of energy. We all know that. We're going from gas to electric cars and stuff. And so we got to talk about power. You hear the term wattage all the time. You're going to hear that constantly here, if you haven't already. And that's basically the product of the voltage and the current. Okay. So basically the simple formula to get the wattage, you multiply the amperage times the voltage, or P equals I times E. Now remember the acronym PI, P-I-E. Let me talk a little bit about direct current. Direct current flows in only one direction. Typically, a direct current will flow from the cathode of a battery through the circuit, through the resistance, and through everything else in the circuit, and then back to the positive, or what they call the anode of the battery. Now, there's another type of current that does not flow in one direction. It's called alternating current. And it reverses direction instead of going from positive to negative. I mean, it does for a fraction of a very short period of time. Then that reverses and goes the other way from the terminals reverse, or the polarity reverses. And that's in radio. Everything in radio, as far as radio frequencies go, that's all about alternating current. Basic circuit, we have a power source. I'm just showing a DC circuit, so you have a negative. This is basically the symbol for a battery, and we'll be introducing you to schematic symbols here. So electrons flow from the negative terminal of a battery through the wiring, through some kind of a resistor, and then back to the battery, which is the positive terminal. Again, remember the symbol is E for voltage, I for current, R for resistance. Just a couple of pictures of direct current sources. A typical one is batteries, okay? You're gonna see that in most circuit diagrams, they're gonna be powering it with the battery. Here's a couple of examples, some AA cells. Here's a lithium polymer out of one of my drones. You can also actually derive direct current from these little devices called power supplies. A power supply will give you direct current from an alternating current source, very convenient. And when you get into operating procedures, you'll hear more about that as well. As far as alternating current, of course, the one that everybody has is the AC socket in your house here. You have two terminals up here. These will provide the alternating current. It actually alternates 60 times a second and delivers power to the load. Another one is a signal generator. This operates as a much higher frequency, typically in a kilohertz or megahertz range. This one happens to be an Elecraft signal source. You use this type of equipment to align and adjust radios with it. Let's talk about frequency. You've already heard that term. Frequency has a measurement, a unit of measurement called the hertz. And that one comes from Mr. Heinrich Hertz. He's a German physicist back in 1857. He lived between 1857 and 1894, a golden age preceding the modern era. It's basically how many complete cycles per second that is. And what happens in a circuit, at any given point in the circuit, the voltage goes from 0 to maximum positive, back to 0 to a maximum negative, and back to 0. And when it's done that, that's considered one cycle or 1 hertz. Here's a little diagram of it here. You have a timeline here. I made this timeline in microseconds. So each unit's a microsecond, or each of these major units is. And this happens to go up to 1 volt, back down through 0 to a negative 1 volt and back to 0 in something like 0.75 microseconds. And then it does it again and again and again. This one, if you notice, and I'm getting a little ahead of myself, it completes 3 of them in 4 microseconds. And you don't have to memorize this yet, but that's a 750 kilohertz signal that you're looking at here. But anyway, it does this. This is called a sine wave, by the way, and you'll hear more about this as you progress. I want to speak a little bit about insulators and conductors. Electrons or electricity needs a material that has free electrons in the atomic structure. And materials that have that are your typical metals, such as copper. Copper is probably the #1 most popular type of conductor, but you can also have gold, you can have silver, you can even have steel, although it's not as good a conductor. Looking at this side, these are insulators. These are materials with no free electrons. Items such as glass, ceramics, plastics, wood to a lesser extent, but anything that's used in the construction of electronic devices where you want to prevent a current from flowing, you use an insulator. Now let me delve a little bit into the mathematics here. I'm going to start with unit conversions. We got to have some knowledge of that, and there's going to be probably at least one or two on your exam. I'm going to cover them, all the ones that are on any possibly can be on your exam, like in the question pool. But they go from a very large quantity of something, and this could be affixed to any unit of measurement. But if you put the word giga in front of it, it means there's 1 billion times whatever one unit was. So if you're talking about a gigahertz, that's 1 billion hertz or 1,000 million hertz. Okay. A mega is 1 million times the unit. So a megahertz is 1 million hertz. A kilo is 1,000 times the unit. Let's say a kilovolt is 1,000 volts. Centi, we don't really use that. I don't know how that got in there, maybe in centimeters, that's 100th. Now we're going small here. So we're going a fractional unit. A milli is the 1,000th of a unit. A micro is the 1,000,000th of a unit. A nano is a 1,000,000,000th. And a pico is a 1,000,000th of a 1,000,000th, very small unit. And we actually do use these for some of our values in here. So let me move on. Here's some examples that you might see. I'm not really doing test questions except for the problems here, but you will encounter these when you review the pool. These are all the ones that I found in sub-element 5 in the tech pool. So you might get one of these, but just for reference, 1.5 ampere is 1,500 milliamperes. 1,500 kilohertz is 1,500,000 hertz. 1 kilovolt is 1,000 volts. A microvolt is 1,000,000th of a volt. 500 milliwatts is equal to 0.5 watts. Okay, there's 1,000 milliwatts per watt, so it's a half a watt. 3 amperes is 3,000 milliamperes. 3.525 megahertz is actually equal to 3525 kilohertz. 1 million picofarads is equal to a microfarads, and I've seen that in a question. 28,400 kilohertz is actually 28.4 megahertz, and 2.425 gigahertz is actually 2,425 megahertz. I pulled all of these numbers out of the pool questions that are in that sub-element. Okay, let me talk a little bit about decibels. You might get a question on that. The reason that we have decibels is that the ranges of a measurement in electronics can really become unmanageable. For example, if you look at a receiver, you look at receiver specifications, you can have anything that goes from, a 10 billion to 1 in actual signal strength, huge dynamic ranges. So it's far easier to quantify this on a logarithmic scale than a linear one, and that's what the decibel is. So let me bring up some examples here. First of all, there's a formula. Please you don't have to memorize this. I just put it up there for your edification. But there's a couple of decibel questions on the pool. One of them is if you increase 5 watts to 10 watts, what's the increase? Well, that answers 3 decibels. And the takeaway from that is when you double anything, you double the power, the increase is 3 decibels. Let's take one 12 watts down to 3 watts. That's what, a 4 times decrease in power. Well, if doubling or having a power is 3 decibels or minus 3 decibels, when you go to 12 to 3, you're having it, and then you're having it again. So you can drop it minus 3 dB, and you have it again down to another minus 3 dB. That gives you minus 6 decibels. And that's the kind of stuff you have to remember. So 4 times decrease is minus 6 decibel, or 4 times increase is plus 6 decibel. The other relationship, which is really cool, is a 10-to-1 ratio. If you look at the last example down here, if you take 20 watts up to 200 watts, that's a 10-fold increase that's a 10 dB increase. And if you want to take that a step further, 20 watts up to 2000 watts, believe it or not, that'll be a 20 decibel increase. I put a little chart together just to show how the changes occur. On the x-axis down here, that's the actual dB change. And on the y-axis is the power multiplier, either up or down. I kind of made this bias to show an upward increase. So if you look at a 1 dB change on the y, or a 0 dB change on the y-axis here, the 0 is up here, and that's a 1-fold increase. So it's basically the same. And when you go up to doubling your power, you go across here and you notice that's an increase in 3 dB. You go up to quadrupling your power, you go up here and that's a 4 times or a 6 dB increase. When you go up to a 10-fold increase, that goes out here. And you notice this isn't a linear curve, it's sloped. And this will go up if you carried this all the way up to 100 watts. When this gets up to 100 watts, this curve would intersect this axis out here. Actually, it intersected the 20 dB axis out here. So anyway, that's how decibels work. Let's talk a little bit about resistance. One of the things that you need to know is resistors affect both alternating and direct current, okay? And most of the stuff at the technician level is going to be concerning pretty simple stuff, direct current, as far as looking Ohm's law. When you get up to your general and advanced and extra class stuff, then you got to start working a lot more with AC and phase angles and impedances and all that stuff. The good news is here is they're not going to trouble you too much with it at the technician level. And the math is pretty easy. A resistor is a device, it opposes the flow of current. Here's a picture of one. A piece of wire actually has resistance, but it's very small, but there is some in there, and it's good to know that at some point. So anyway, there's some schematic symbols for resistors. It looks like that. You'll be hearing more about schematics. There's a type of resistor that's variable, that you can actually rotate a shaft. And if you look at what's behind most knobs on radios, you got a device like this sitting behind it. And basically, it works by turning there's kind of a wiper thing in there that goes along the length of this, and it varies the resistance between these 2 points or these 2 points. So anyway, that's what a potentiometer is. You'll hear more about components and schematics later. Typically, these are used for volume controls and other things. I want to introduce inductors. That's another thing that they talk about in this section. An inductor is basically a device that stores energy in a magnetic field, okay? And, if you don't know anything about electricity, it's kind of hard to get your hands around. But first of all, the inductors typically a coil of wire. Sometimes it has something in the middle of it that increases the magnetism. But, if you remember, maybe in your grade school science, if you made an electromagnet, you can wind a coil of wire around a nail, you put a current through it, and it becomes magnetized. Well, inductors do that. But the interesting thing, they don't do much with direct current. Direct current just kind of passes right on through them. But alternating current, that's a schematic symbol down here, by the way. I guess the best analogy, I think, would be to think of something mechanical, okay? A direct current is just a spinning wheel, spinning one direction all the time. But if you picture a flywheel, something with some mass to it, you'll notice that if the thing is at rest, it takes a little force to get it going, okay? And if you think of an inductor, when you have current begin to go through it, it takes some force to build up that magnetic field, okay? But then when the current gets to a constant value, the current will just flow through very little. It might have a little resistance, but the current will flow through. But when you interrupt that current, you open the circuit up, then the magnetic field collapses and it induces more current through it. And that's a property we can use when we get into electronics. The unit of measurement on that is the Henry. And that one was named after Joseph Henry. He's actually an American. We have a real international cast of characters. He was born in 1797, died in 1878. Another guy from that golden era. I also want to talk about capacitors a little bit. What's a capacitor do? It basically is a device that stores energy in an electric field. Again, these are mainly used in alternating current circuits because they have some interesting properties. They're basically consisting of two or more conductive surfaces separated by an insulator. You'll hear more about that later. There's a picture of what the device might look like. There's all kinds of these. You can have them fixed. This one's an electrolytic. But in a circuit, what they kind of act like, if you want to think again of a mechanical analogy of something like that, think of a spring, okay? When you push against the spring, at first it takes very little effort, you know, if it's the right kind of spring. But then as you push further, it gets tighter and tighter, and pretty soon you can't push anymore. And what happens in a capacitor, if you apply a direct current to it, the electrons will rush in on the negative side, and the electrostatic field between them will actually draw positive charges to the other side. And that will cause some current to flow until the capacitor gets to a state of equilibrium, and then nothing will flow. So they kind of work the opposite of an inductor. And the cool thing, if you think of those two mechanical analogies, on one side, think of the old-fashioned wristwatch or an old-fashioned clock that you wind up. If you ever taken one of those apart, when I was a kid, I used to take them apart all the time. You got a thing in there called the escapement, which is a little flywheel, and there's a little spring sitting right on top of it. And it goes back and forth. And you know, if we'll get to this when you get, I think you'll get into that in your general Q&A. You don't get too much into resonance and technician, but a capacitor and a inductor in parallel will actually act like a movement on a watch, and you'll actually get an AC that'll go back and forth, and the frequency of that is kind of determined by the values, how big the capacitor and the inductors are. So anyway, that's a little bit about that. The unit on a capacitor, by the way, is the farad. You might have heard this term when I was talking about the units, and that's named after Michael Faraday. He was an English physicist. He lived between 1791 and 1867. All of these guys were in that same era. That's amazing, isn't it? I want to talk a little bit more about power. I mentioned that earlier, P equals I times E. When you come to these little relationship formulas, I like to draw a circle. I have a better one. Actually, Adrian made it for doing the basic Ohm's law, but for the power formula, think of pi. You put P on the top here. If you memorize the circle, you put P on the top. So if you cover up the P, let's say, you multiply the I times the E, okay? So you can find P. If you don't know I in an equation like that, then you cover up the I, you divide P by E, and you get the current that way. Or E, you can divide P by I. So that's one way to get it. Fortunately, I think there's a pretty small chance you're going to get a power question, although there are two in the pool. In fact, here they are. I think there's three in the pool. You're given 10 amps and 13.8 volts. How much power is dissipated by that circuit? Remember, P was on top, so you multiply I, which is 10 times E, 13.8 times 10, you get 138 watts. Given 2.5 amps and 12.0 volts, how much power in the circuits? 2.5 times 12 or 30 watts. Those two are in the pool. Those two questions. There's one more question in there, and this time you're given the power at 120 watts and 12 volts is given. So now you got to solve for current. So what do? You cover up the I, so that's P over E. So you take your 120 divided by 12, and you end up with 10 amperes. Okay, we're going to talk a little bit about the magic circle. This is, you got a number of more problems, very simple problems in Ohm's law. Most of them you're just given one of the given two of the variables you need to solve for the third one. So let's go through how to get this done. To find the current, you cover the I just like that. Okay. So I equals E divided by R. Again, E's on top, the R is on the bottom. If you want to find the voltage, you cover up the E like that, and you multiply I times R. And if you want to find a resistance, you cover up the R just like that, and you divide E by I, and that's how you get it. So let's go into a little bit of Ohm's law practice here. We have just a basic DC circuit. So you're given a current of 1 amp. You're given a resistance of 10 ohms, and you're asked for the voltage. So E equals what? Well, E equals I times R, or 1 times 10, and the answer is 10 volts. Okay, let's say we're given a resistance of 100 ohms, and you're given a voltage of 200 volts. So what's the current? Okay, well, I equals E over R. So you just simply divide 200 by 100, and you're given an answer of 2 amps. Easy. You don't need a calculator for this, and these are right out of the test pool, by the way. Let's say we're given a current of 3 amps and a voltage of 90 volts. What's the resistance? Well, R equals E over I. So you just take 90 divided by 3, and voila, you get 30 ohms. And this little symbol, by the way, the omega symbol, is the symbol for ohms, just for your information. There's a few other formulas. They don't really quiz on this, but there's some other relationship if you combine the power formula and basic Ohm's law that I just discussed. Here's 3 other derivatives. The good news is you don't have to, for the tech exam, you don't have to extract a square root or even square anything. But these are the formulas here. Let's just do some simple practice questions. What's the voltage across a 10 ohm resistance if a current of 2 amperes is running through it? Okay, so E equals I times R. So the answer there is going to be 20 volts. Going through this one, what's the voltage across a 2 ohm resistor if a current of 0.5 amperes flows through it? So you take, let's see, you're looking for voltage. E equals I times R. R is 2 and 0.5 is I. So 2 times 0.5, that's 1 volt. Okay, what's the current in a circuit with an applied voltage of 120? So we know the voltage now, and a resistance of 80 ohms. So we got to go I equals E divided by R. So, you take 120 divided by 80, and that's going to give you 1.5 amperes. So the answer is D. Okay. And these are right out of the pool. What's the current through a 24 ohm resistor connected across a 240 volt source? Okay, I don't see the right end of this slide. It's cut off on me. So let's see, that's TD09. I equals E divided by R. So E is 240 divided by 24 ohms, and that's going to be 10 amperes C. Okay, what's the resistance of the circuit for which the applied voltage is 12 volts and the current flow is 1.5 amperes. So R equals E divided by I, so 12 divided by 1.5, and that's going to be 8 ohms C. And the last one here, R equals E divided by I. What's the resistance of a circuit that draws 4 amperes from a 12 volt source? So R equals E, which is 12 divided by I, 4, and the answer is going to be A, 3 ohms. But anyway, we're getting just about to the end. It looks like time is working out pretty good for our favor here. Just a little note, there is some mention of series and parallel circuits in the sub element. That's an example of a series circuit. You have a power source. This little symbol up here is an ammeter, and there's 2 resistance. You got to remember something about anything about an electric circuit. There's only one path in this one. You know, you got electrons going to go all the way around and go back to the other side of the battery over here. So current, you know, you got to remember that's a flow of electron. It's going to be constant everywhere in this circuit. It's going to be constant. The only thing that's going to vary is if you were to go and actually take a voltmeter and measure the voltage drop, there will be a difference in drop across each resistor, but the current's going to be the same. Okay. We'll compare that to a parallel circuit. You know, you have a voltage source over here measured here. And if you look at the current, because the electrons are going to come and some of them are going to go this way, some are going to go this way, and then they're going to come back together down here. So you're going to get partial, you're not going to get the same current through the whole circle. You're going to get part of the current going through here, part of the current going through here. If these 2 resistors are equal, these currents will be the same. If they're different, there's going to be a difference, and there will be more on this later for you. But anyway, I think that completes the section here. Does anybody have any questions? Any questions?
Is anybody still awake?
Yep. Still here.
We followed it. Interesting.
The cool thing about all of that is, you know, I can give you an analogy. Yeah, you study for this stuff for your ham license, but you know, there's a lot of real world places where you can use this information. For instance, as you proceed in your amateur radio endeavors, you know, you might want to at some point hook up get a more powerful radio to put in your vehicle. Okay. And vehicles typically, unless you're driving a Tesla or some electric, your typical gasoline powered vehicle has a 12 volt electrical system. And, you know, you have to have an understanding of Ohm's law to be able to correctly wire something like that up. You know, you're going to have to, let's say you do the job yourself. As an amateur, a lot of us do those ourselves. And you have to have an understanding, and you have to know that, for instance, wire itself, you know, yeah, I showed a picture of a resistor, but a piece of wire has resistance too. It's not very much, but it does have resistance. And if you use too small a piece of wire and you look at those formulas, and you start ramping up the current, you know, some of these radios, when you key, you know, transmit, will draw 20 amps, you know, 15 amps, 20, even 25 amps. And if you have a piece of wire that even has 1/10 of an ohm resistance in there, if you do E equals I times R, so if you take 40 and you multiply it times 0.1, let's say, or let's say 20 times 0.1, that's 2 volts. And what that means is that radio, if you got a thin piece of wire that has 1/10 of an ohm resistor, that radio, even though your battery's, let's say, putting out 13.8 volts, the radio might only see 11.8. It might not function. So a knowledge of Ohm's law, that's why they have this in here. Okay. There's all kinds of examples you can think of. Dave, you're saying something, but I think you're muted.
You're absolutely correct. So I have another example that just came up yesterday. Jane and I are hunting for a new dishwasher. And we went out to the appliance store to get a new dishwasher, and it had one model that was touted to be very quiet, and another model that was kind of at the noise level that our current dishwasher has. And the salesman turns around and says, see, this one has 42 dB of noise, and this one over here has 39 dB of noise. And Jane pops up and goes, oh, well, that means it's half as noisy because it's 3 dB down, which means it's 1/2 as much noise. And the salesman was absolutely totally confused that Jane knew that 3 dB was either twice as much, and minus 3 dB is 1/2 the amount, because dB is also used for noise measurements too.
Yeah, anything, yeah. The interesting thing, Dave, on that note, is that the ears and the eyes, when it both comes to visual perception and light levels and audible levels, they're actually logarithmic too, though. So when you're doubling the sound pressure, you don't hear it that way. If you think about it.
So anyway, your ham radio expertise will come in handy in many different areas.
Yeah, I had one more example. When I first bought my first toy hauler back in 2007, I had a squawk with it. I brought this brand new trailer, and I took it on my the maiden voyage. I went dry camping with it. I don't know how many of you have RVs. I took it out dry camping, and the battery went dead. I mean, I charged it up for a week. Battery thought it was charged. Thing brand new under warranty. I took it out on a camping trip, and I woke up in the morning and the lights were like dim and the water wouldn't flow, nothing worked. I said, this ain't right. What's up with that? Brand new battery, water's good, everything's good. And anybody that has an RV knows that the quality and workmanship in those things, you watch any of I'm a big RVer, and some of you might be. The quality on those things, horrible workmanship and everything is really bad on a lot of them. Well, make a long story short, I took it back to the dealer. It was under warranty. I said, this thing ain't charging up. Please fix it. And he pulled out the first thing the guy did, he pulled out the charge controller. There's a device in there that it's like the power supply I show you that keeps the battery charged when you got the thing on shore power plugged in. And it wasn't charging the battery. During a camping trip, I run the generator around the clock, it still wouldn't hold the charge. So I got to thinking, I went back to the dealer, and they told me they had, after leaving it 10 weeks, and that's typical, they couldn't find a problem. They replaced the charge controller, and it still did it. I got to thinking, Ohm's law. And I took a look at the wiring in there. Okay, from the charge controller, they had like number 10. They had like 2 or 3 crimp-on connectors. They had a fuse, and they had a cutoff switch and a bunch of other stuff. I measured that. It was about 0.2 of an ohm for the whole enchilada. I got to thinking, that charge controller rate of 40 amps times 0.2. Ohm's law. And guess what? The battery wasn't seeing, but it wasn't charging at all. It wasn't seeing enough voltage from the charger. So I went down to a welding supply shop, ripped all that stuff out, put in, I think double aught cable. Problem went away. That's Ohm's law, practical application. You do solar, you do any kind of wiring, it comes into play. Are there any more questions? Hopefully I don't have everybody bamboozled.
Go to sleep.
Or as I say, if you're double A, you're probably having your third beer.
Linda's talking, but
Who's talking?
Linda, but she's muted.
Okay, yeah, Linda, you're muted.
She does that a lot.
Have you ever wished that you could mute somebody in real life?
I was just going to mention that the two practice test sites that I mentioned, I put the links in the chat.
Yeah, did you put in a ham study? That's a really good one.
No, these are two other ones, EHAM and QRZ.com.
Yeah. Let me drop a ham study one in the chat as well here.
And Steve, if you're still on here, I transferred host over to you. And so at the end of this call, you should be able to save the chat and save it to a file that you can actually include as an attachment and then email back out.
So you're saying you turn me over to the host and I should be able to save it somewhere?
Oh,
Oh,
Steve Aberly. Yeah, we're gonna have to number you guys. Steve Aberly, Steve A.
No. I asked the same thing about being able to save the recording. Oh, I'll just call myself Steve W.
You are now officially Steve W.
Okay.
Maybe just
No.
click up on the three little things up in the upper right-hand corner, rename yourself too. That makes it easy.
Well, I noticed that she transferred host over to me, so I did rename him. So I could keep track of who's who. So we have a presentation supposedly by K7LCW, but I don't see him on the call yet. I just emailed him about 5 minutes ago or 10 minutes ago. I said, where are you? And so that part of it doesn't look like it's going to happen.
What were we going to discuss?
What's
We
this?
can make an open forum out of this. Just
What's the subject?
Basic radio go kits.
oh,
Oh,
I can turn my camera around here. I got one sitting next to me. It's sitting right there. I built
Hey,
that one.
Steve, is that with JD?
Yeah,
okay.
JD called earlier and he did say that he didn't have an external camera. So he didn't think he was going to be able to do the go kits if he wasn't able to show them at the COI.
oh, okay, I see. Did he drive all the way over there?
No, he called me before he left his house.
Oh, okay, good.
Yeah. So maybe he asked me if he could do the go kit another night of one of the classes. And I said, yeah, I thought we were doing FCC rules tonight as well. So I might
You
not
have
have
to
realized he was.
To separate the stuff that's in there for the license, and then there's the extra stuff that we've got that just helps you become better at what you do.
Yeah.
And so the
So
go
he did ask
kits,
if he could do that another night.
oh, okay. Yeah, we'll reschedule them.
Yeah.
And
Well, I
do
thought this
have
was really
all-
good tonight.
Yeah, I do have all the slots filled for the class instructors, like filled the last one earlier this evening.
You mean for the exam?
Perfect.